Okay, good morning. So some folks are still finishing up the quiz, and that's fine. Take another few minutes to finish the quiz. We'll go ahead and get started if you're already finished. So if you're ready, you can open to page 41. And while we're opening to page 41, we'll have our look at the calendar. Last class was our derivatives overview, lots of hard derivatives, putting all of those derivative rules together. Today we're finishing up quiz 5 and we're tackling implicit functions, which is the last section before the test. So in theory, on Monday, we're going to have our review day, and in theory, on Wednesday, we're going to have our test. And I say in theory because there's some meteorological craziness that's happening right now. I'm going to talk about the possibilities, but I want to make sure everybody hears that. So I'll wait for people to finish the quiz before I talk about what might happen next week. But we'll go ahead and start on page 41, which is actually not the beginning of this section. We're going to jump around a little bit. But on page 41, we can see this very, very pretty curve. And I don't know how it shows up on your paper, but that diagonal line there is not part of the curve. That's an asymptote, right? So the curve gets really close to that line, doesn't actually hit it, but it's just there to show you that it's leveling off in some sense, even though it's not a horizontal leveling off. Okay, so what's unusual about this curve compared to all the other curves that we've looked at this semester? It loops, which means what's the word that we cannot use to describe this function? Function. We can't use the word function to describe this curve because of that vertical line test, right? For example, there's a point here, which corresponds to x equals, say, 1.5, and then there's another point over here. So it's like 1.5, comma, I'll just make it up, 0.7, and then maybe up here, 1.5, comma, 1.5. So there's a vertical line. It hits the curve twice. There are a lot of vertical lines that hit the curve twice. So that's not a function. That said, can you guys go ahead and put a dot right up there at that kind of extreme upper right point? So put a dot right there and draw a tangent line. Does the curve have a tangent line at that point? Sure. You guys can draw something. Maybe it looks downhill, something like that. Okay. Yeah, and Chris points out maybe it's parallel to that other line that's going there. All right, can you guys go ahead and put this other point on there, the one that's kind of straight below? I don't know exactly what the coordinates are, but 1.5, comma something, and then draw the tangent line at that point. And the curve has a tangent line there, and that one's kind of uphill and maybe a little bit steeper. So we still have tangent lines for every point on this curve, agree? Every single point on that curve has a tangent line. Well, there's actually one point that's kind of funky. What's the one point? Yeah, the origin. It's not really clear what's happening there because the origin is at that intersection of the two pieces. And so, you know, like on the one hand, if we're coming in this way, what does it look like the tangent lines are doing? It looks like they're getting steeper, like vertical. But if you happen to be coming in this way, what kind of tangent lines would you draw? Like really flat horizontal. So, okay, fine. At that point, maybe it doesn't have a tangent line because that's where the thing hits itself. But I feel like every other point has a perfectly good tangent line, even if it's not a function. So the goal of today is to be able to find the slopes of tangent lines, even when the thing is not a function, all right? That's the goal. And so what that means is that, so we're used to writing dy dx equals, and then there'll be something with lots of x's in it, right? That's my way of writing formally, something with lots of x's. Could that be the case for this curve right here? Is it going to work that the derivative, the slope of every tangent line is going to be something with only x's in it? Well, what would happen if that were true and you plugged in x is 1.5? There's two different slopes at x equals 1.5, right? So it can't be the case that our derivative is going to look the way they've looked all semester. I can't just have x's in here. What else do I have to have in here? It's got to have y's in it. But I need more information. You can't just say what's the slope when x is 1.5 because there's two different points when x is 1.5. So it has to be the case that there are going to be y's floating around in this thing too. So this is the new derivative for today. It's going to have x's, and it's going to have y's in it. So it'll look quite a bit different than the derivatives did before. So let's give this a shot. Here's the equation of that beautiful curve right there. X cubed plus y cubed equals 3xy. And what I want to do is find, it says find the equation of the tangent line. And we're going to use the point over here, 3/2, comma 3/2. That was the upper right point that you guys plotted first. Okay, so in order to find the equation of any line, what two things do we need? A point and slope, right? One of those is given. That's the point. It's 3/2, comma 3/2. We also need to find the slope. Slope of a tangent line is the derivative, so I need to find the derivative. So let's go ahead and write this equation again. X cubed plus y cubed equals 3xy. Then I'm going to put the same thing in front of both sides. You guys know what that is? What do I want to do to both sides? Take a derivative. I want to find dy dx, so let's take a derivative of both sides. So d dx is our Leibniz way of saying take a derivative. Okay, so since we haven't gone too far into this one and everybody just finished the quiz, I'm going to go ahead and pause this and we'll just talk about what might happen next week. So in theory, according to our calendar, Monday is our review day, Wednesday is our test, Friday is a new section, okay? I don't know what's going on with this weather. I don't really follow these things too carefully. It still feels like it's far away to predict anything for Monday or Tuesday, but apparently this is some unprecedented like combination of forces, and I don't know. So I don't know exactly what classes will be canceled next week, if any, but I made a little chart. So if all the classes are open, Monday, Wednesday, Friday, then Monday is our review day, Wednesday is our test, Friday is the new section. That's what it's supposed to look like. If just Monday is canceled, normally I would just pick everything up and shove it to the right one day. And we do have a day that's available. I'm not going to do that if Monday is canceled. If Monday is canceled, we're still going to have our test on Wednesday. And that's the one that I really want to highlight just in case, so that nobody comes in Wednesday thinking it's going to be a review day pushed back. And the reason I feel comfortable doing that is that on our review day, generally, you guys just sit there and work on the sample test problems. And if you have Monday off, then sit at home and work on the sample test problems. The videos are up on YouTube. I will show you in just a minute how to find them. But I feel like because they're up on YouTube, you guys have that resource. You could. Okay, so if we don't have power, then that's another concern. Yeah. So if Monday is on, then that will be our review day. And then if Wednesday gets canceled, test gets pushed back to Friday. Okay? If both of those days are canceled, test is Friday. Monday's on, it's a review day. I don't. So like you get the idea, right? Like if our review day is canceled, it doesn't bother me. We're having the test the next time that we meet. Okay? The test will not be on Monday no matter what, but it could be Wednesday, it could be Friday. I guess it could be the week after. I really don't know what's going to happen. Everybody understand the basic idea? Okay, so given that we might not have our review day, can we just jump real quick to page 52, the last page of this packet? Okay, I want to be clear. All of the test is calculator active. You are again allowed to bring a one-page sheet of notes of your own creation, anything written or typed by you. You might want to save that for the final exam. You are also going to rip the first page off of this packet when you come to the test. That's the derivatives formula reference sheet, okay? So you'll actually have two pieces of paper in your hand when you take this test. It's intended to be a 1-hour test. I'm going to give folks some more time if they want it. Your window is 8 until 10, whatever day we happen to have that test. Okay, so instead of showing up at 8:40, if you want some extra time, show up at 10. Okay, let's see if we can find those sample test problems. If you find them before me, let me know where they are. Okay, page 44. On page 44, you'll find our study guide for test number 2. It's got a whole bunch of things that we'd like you to be able to do. It's got some problems that you probably haven't looked at yet that you can practice. You can also look at old homework assignments and quizzes. And then finally, the sample test problems are on the next page, 45. So the sample test problems are here. They go for a few pages. Eventually you'll find an answer key. And that is on page 51. So the answers are all typed up there. But in addition to the answer key, again, I went through and solved all these sample test problems and put them on YouTube. I also made the PDF of my solving all these problems. So if you actually want to see my work written up on the thing in color and everything, just go onto Moodle and you'll find the PDF for the sample test problems. All right. So not just the solution, not just the answers, but the solutions. And then finally, the sample test problems are really easy to find if you know what you're typing. And if you don't know what you're typing, then you might never find them. So if, for example, you want to look at problem 4 on the sample test problems, this is what you type. No spaces, 201 sample test 2, problem 4. And if you hit enter, you'll find this is the problem that you want, and it actually links to the rest of the sample test problems. There's the full playlist there, okay? It's easy to find if you know what you're looking for. There's also a link on the syllabus, which I gave out on the first day. Any questions about any of that? Any predictions? Monday off, Wednesday off, Friday off? What do we think? Nothing. Chris? For instance, not to be alarmist or anything. Yeah. So I don't know. I don't know what to say. I still feel like it's very difficult to predict things. You know, even 24 hours out, and we're predicting further than that. Yeah. I mean, it's hard to know what's going to happen. Just stay safe, and you know, I mean, like if the school is open, but it is not safe for you to get here, then don't come. You know, figure it out when you're able to get here. If you can call me or email me and let me know, hey, I couldn't make it today because my house is now on an island and you know I can't swim. So just contact me in any way that you can as soon as you're able if you can't make it in when we're open. But be safe. All right, so let's come back and see if we can do the rest of this problem. So we're back on page 41. Oh, I see. Okay, page 41. So the goal is to find the slope of the tangent line. That's the green one, not the black one that I drew. So we want the slope of that line, so I want a formula for the derivative. So we'll take a derivative of both sides of our equation. So here's where it gets a little bit interesting. Okay, so first there's a sum. Are sums good or bad for derivatives? Very good. So we know it's going to be a plus sign in between. What's the derivative of x cubed? 3x squared. Easy. Nothing new. Plus, what's the derivative of y cubed? 3y squared. Nothing new. Except there is something new. What if it was just y equals x squared? What would you write? Okay, so I know the derivative there is 2x. What would you write over here? You'd write y prime, right? So you know that the derivative of y is y prime. So, but if it were just something like x equals, what's the derivative of x? The derivative of x is 1. The derivative of y is y prime. They're not the same. We can't just look at them and say, oh, the derivative of a single letter by itself is just 1. We have to recognize that even if we can't solve this equation that's circled in black, even if we can't solve that for y explicitly, even if we can't get y equals, still in our minds, y is, I guess not a function of x, but y is related to x. X is still the input, the independent variable, and y is still the output, the dependent variable. And so they don't just behave the same. So in my mind, I'm thinking that y, this y right here, is some function of x. It's got x's buried in it, even if I can't find that rule explicitly. So when I take the derivative of y cubed right up here, let's see, this y in some sense is kind of like some stuff. So that's really some stuff cubed. So what's the derivative of stuff cubed? It's 3 times the stuff squared. We've got that, 3 times y squared. But then you got to tack on what? Derivative of the stuff, right? This is the chain rule. If you have some stuff that's getting cubed, you got to tack on the derivative of the stuff. So what's the derivative of the stuff? It's y prime. This would be explicit if we could write it as y equals f of x. We can't, but I'm just kind of highlighting that in our minds, y has lots of x's in it. And so when you take the derivative of y cubed, it's really taking the derivative of lots of x's cubed. And so that's the chain rule coming down here. Okay, so what do we think? Derivative of x cubed is 3x squared, nothing new. But the derivative of y cubed is 3y squared times y prime. X and y are not the same. Okay, that's that. Let's try the right-hand side. Equals 3xy. What rule for finding the derivative? That's the product rule. It's the multiplication rule. I'm going to go ahead and circle 3x will be my first term, and then y can be my second term. And let's go ahead and find the derivative using the product rule. So we go first times derivative of the second. Copy the first times, what's the derivative of the second? It's y prime. It's not just 1. Anytime you're taking a derivative of something with y, tack on that y prime. In this case, it's pretty much the only thing to tack on. It's y prime. That's the first part of the product rule. Plus second times derivative of the first. Second is y times 3. Now there's going to be a bunch of algebra to do, but really the calculus is done. So how about we put that algebra on hold, and I just want to do another example real quick just to really drive in this idea that x and y don't behave the same. If you're taking a derivative of something with y, you do it normally, but then you tack on a y prime at the end. The chain rule comes in every time. So let's go back a page. And I want to look at this equation right here in the middle. X equals y squared plus 1. And what we're going to do is take a derivative of both sides. So can you guys in your groups take a derivative of both sides and write down some brand new equation? Okay, what's the derivative of the left-hand side? That's just 1, that's normal. Equals, what's the derivative of y squared? 2y, times y prime. That's really the heart of the new idea for today. So if you take a derivative of x, it's normal. But if you take a derivative of something with y, do it normally, and then tack on a y prime at the end. And this one, actually, the algebra is easier, so we'll just do the algebra. The goal generally for us has been find the derivative, find y prime. So can you guys solve that equation for y prime? What should we do to both sides to get y prime by itself? And divide by 2y. So we get 1 over 2y. There you go. In this case, the derivative is 1 over 2y, which is the first time we've ever seen a derivative look like that. What's unique about that one compared to every other derivative we've seen? All right, so it doesn't have any x, which is okay, but more interesting, it has y's, right? It's the first time we've had a derivative where the function, the answer, has y in it. But that's it. That is the derivative of this function. It's 1 over 2y. Okay, let's come down here. Let's look at this guy right there. Can you guys, in your groups, and this one will be a little longer, so maybe about a minute. Sine of xy equals y. Take a derivative of both sides. Take a derivative of both sides. Okay, so I've written what I got on the smartboard. So this is a sine of stuff. It becomes cosine of stuff. So that's the first part in blue, and then times the derivative of the stuff. The stuff is xy. What rule do we need to use for xy? That's a product rule. So we use the product rule first times derivative of the second. What's the derivative of the second? It's y prime. So that's right there. and then plus the second times derivative of the first, y times 1. And then the derivative of the right-hand side, don't forget, you're taking derivative on the left. You have to take a derivative on the right as well. And the derivative of the right-hand side is just y prime. Questions on that? Okay, well, let's see if we can go back and finish that problem on the next page. Again, the goal is to find y prime. Now we've taken a derivative of both sides, but we've got y primes floating around and we want to get them together so that we can get a y prime equals. So again, the rest of this is just going to be algebra. It doesn't mean it's easy, but it's just algebra. Solve for y prime. That's the goal. So how many y primes do we see? We see 2. Let's get the y prime terms on one side. Let's bring them to the left. Doesn't matter. And then the terms without on the other side. So what stays on the left? I'm going to bring the y prime terms to the left. Okay, so the y prime term stays on the left. What other term comes to the left? It's the 3xy prime. Subtracting that from both sides. What term is still on the right-hand side? It's the 3y. What term moves to the right-hand side? 3x squared. So make sure you're okay with that algebra. So the thing without the y prime goes over here. The thing with the y prime goes to the left. You could choose to move them to the right. Doesn't matter. Everybody okay with those 4 things? They're still all there? Okay, now that we've got all the terms with y prime on one side, what can we do? We can factor it out. That's why we put all the y prime terms here and everything without over there, so that we can factor y prime out of both. So go ahead and pull a y prime out. And figure out what's left. So what's in the parentheses? Good. And then finally, I'm going to solve for y prime. So we'll divide both sides by the parentheses. Yes, you can cancel out the 3's. You could factor 3 out of the top and 3 out of the bottom and then cancel. Absolutely. And again, what's very strange about that derivative? It has y's in it. I'm used to saying y prime equals something with x. Now I have to get used to saying y prime equals something with x and y. All right. So here's the technique. I'll just say in English what we did, but hopefully we remember here. We took a derivative of both sides. All the x things were normal, but all the y things you have to stick on the y prime when you take a derivative. And then the rest is algebra. Not always easy, but just algebra solving for y prime. And the other thing you'll need to be able to do this question or this kind of question on the test is you need to know when to apply it. So can you look at that equation I circled in black there? How would you know that this is the technique? Yeah, x's and y's, both sides all mixed in together, right? All the other equations we've dealt with this semester have said y equals. Just do a normal derivative. Like on the quiz, you did 3 normal derivatives because they all said f of x equals, or something like that, maybe other letters. But it was always one thing by itself, only one letter. When both letters are mixed in together, This is the technique. That's how you know when to use it. Mm-hmm. Yeah, it's totally valid. If it's possible to solve for y, then you can go ahead and solve for y and then answer the question like you did on the quiz today. Right? But an equation like that would be really challenging to solve for y, and there are other equations that it's just impossible, no matter how good we are with our algebra, like this one down here. You just can't solve that equation for y. All right, so the last thing on this guy, we have our derivative. It's down here. Again, we wanted to find the equation of that green tangent line, which means I got to find the slope of that tangent line. I have my formula down here in black. I want the slope of that particular tangent line at this point. So what should we do? Plug in. 3 halves and 3 halves go in for x and y. Okay, so at 3 halves comma 3 halves, y prime equals, and then we're going to plug in. Instead of y, what are we putting? 3 halves. That's the y coordinate. Minus, instead of x, what are we putting? Also 3 halves. That's 3 halves squared over y squared. 3 halves squared minus 3 halves. And if you think about it for a moment, you can figure out what that is without a calculator. The top and bottom are almost the same, aren't they? They're just reversed. So do you guys remember what you get when the top and bottom are the same, but all the signs are backwards? That's -1. Yeah. I mean, you can type it in or you can calculate it, but ultimately we're going to get a -1. What does that -1 represent in this picture? It's the slope of which line? Yeah, and which one? There's 2 up there. There's the top one, the green one. We plugged in 3 halves, 3 halves. We got the slope is -1. If I wanted to plug in 1.5 and 0.7, although don't do that because 0.7 I just made up. Like you got to plug in the right number. But if you plug those numbers in, you get the slope of the black tangent line. Okay. And so then finally, again, the goal was to find the equation of the tangent line. So maybe we'll do our mx plus b thing. At the point we're interested in, how much is the y? 3 halves. We just did a lot of work to find the slope of the tangent line, -1. At the point, how much is x? Also 3 halves. And then the b you're about to find. Three. So then finally, y equals mx plus b. M is still -1. X plus b, 3.
I'm having a harder time, like, just a regular derivative picture. It's like distance in terms of time, or like units are and stuff. Like, I have a harder time even imagining that.
Yeah, I think as soon as we start trying to think about distance and time, we run into trouble because you know, that means like at a given time you would be in one spot. But in this example, whatever thing you come up with to try to visualize, you got to imagine that at one time there's actually something in 2 different spots. Hence.
Is it like how y is changing in terms of y and x?
Yes. Yeah. How y is changing in terms of y and x. So if you had this point in blue here, kind of driving a car along this funny shaped loop-de-loop track, if that person in blue got around to that blue dot we were interested in and then decided to stop following the track by turning the wheel, but just let the wheel go and went straight, what would that car do? You just go off on that tangent line, the equation that we found. But if you had, say, this person down here driving towards that point, so slightly driving to the left, and then all of a sudden at that point decides I'm not going to steer anymore, they would end up heading off in the direction of the black tangent line. At the origin here? Oh, something about where they intersect. Oh, that's a wonderful question. I have no idea, but this is a great question. We've got two different tangent lines hitting each other. Are there some nice relationships? If you know, like, is there some quick way, like if we just said, okay, x is 1.5, which means both of those points are in play. Is there some quick formula we could use to figure out where the tangent lines meet? You know, like if x is 1.5, maybe the tangent lines meet at 1.8. And if x is, 0.2, maybe the tangent lines meet at negative 0.4. Like some nice little formula that just tell me what the x is and then spit out the formula for where the tangent lines meet. That's a great question. All right, so here's the plan. On the next page starts the activity. It has to do with 4 different curves. So what you're going to do is follow the directions. It says find dy dx and then find the equation of the tangent line. So find dy dx and find the equation of a tangent line. All day today we've been calling it y prime instead of dy dx. It's up to you which one you write. And there is an answer key that follows, but let's see how far you guys can get in your groups.